Well, happy day, folks. We're here for our second and final class of the semester week. Maybe that would be wishful thinking. And it is a rainy day here on the Central Coast, so I hope that you are having a great day wherever you are. If you just give you a couple of reminders here, we've got PLC 6, and that is for Friday. Homework 4, I did post last night, and I'm going to go for Tuesday, in a week from next Tuesday. That would be the 25th, if I'm looking at the calendar correctly. So we will go with that. That's geometric optics. And so that will have some questions and usual selection of problems. And we will get going on plane and curved mirrors today, after having talked about the principle of least time, or at least the principle of zero order change in the time depending on nearby paths principle, which is not as fun to say. So that's coming up. Usual quiz will happen that day, and we'll go from there. All right. And we might have a concept quiz in the meantime. We might have a little concept quiz at some point next week, but not sure on that. So we'll go a little further back, see how it goes. All right. So today, what I want to do is focus a lot more on reflection from mirrors. And we have the law of reflection. So what we're going to do is apply, and we have our mode of thinking about why the reflection is the way it is from Fermat's principle. So we're going to apply this to both plane mirrors and curved mirrors, one either way. So let's take a look here and see what we can do. We'll start here with the plane mirror, and we will begin with a simple situation. However, as we're going through this particular example, I'm going to go through a couple of things that we are going to be assuming throughout the section on geometric optics. So they are pertinent, and I want to bring them up when they apply so that you can see them. But it will be true not just for this analysis, but for all of them subsequent to this, and that includes lenses. Okay. So a plane mirror, we're going to look at reflection. So what I'm going to do is I'm going to introduce the drawing. Okay, we're going to do what's called a ray diagram, or a ray diagram. At least I call them that. They're also called ray tracings, which I'm not sure why, so I'll just put that up here. But you'll often see them referred to as ray tracing. I'm not tracing anything, I'm actually creating a diagram, so I'm not really sure why they're called tracings. But maybe maybe it's because you were tracing the light. They were putting the setup on a bench and then tracing the light out where it went. Maybe that's what it was. Anyways, what I want to do is start off with the diagrams and give you an introduction to what this looks like. So, a plane mirror here. That's a bad start. Let's try this again. Okay, so suppose we have a plane mirror, and right, it's standing on the floor here. By convention, almost every single time I draw an object, it's going to be to the left, and the light rays are going to be propagating to the right. So this is going to be one of those kind of well, I guess it's kind of an assumption, but it's going to be one of those things I'm going to bring up in this case as part of the narrative, but will kind of carry on through all of the geometric optics. So most of the time I have the object over here on the left. And so you suppose that you're standing in front of a mirror. And you have your arms like this, okay? And this entire thing is a mirror, so it's a mirror front, top to bottom. Now, you're standing some distance away from the mirror, and what you're interested in is where is your image going to be? And what the ray diagram is going to do is be able to give you the opportunity to make an approximation, make a qualitative estimate as to what the image is going to look like and where it is going to be located. And you'll see more of that as we get into the curved mirror part. So what I'm going to do is I'm going to freehand this. Normally I would use a straight edge for this, but it looks like I forgot to bring in my meter stick. So what we're going to do is just check and see how well that shows up. That's okay, it's not great. And okay. So I'm going to take a couple of different rays. Now, this is ray optics, so we're assuming, number one, light's traveling in a straight line. Okay, and we have the second part of this, since it's reflection, we know the angle of reflection when it comes off is equal to the angle of incidence when it hits the mirror. So, this being all in air, all the light is traveling at the same speed. And so what we're going to do is we're going to take a point on the person. I'm just going to select the top of the head. Okay? And I'm going to try and figure out where is this image going to be. Now, we already know, we've looked in mirrors, hopefully, you've seen yourself in a mirror multiple times during your life. So we know what we're expecting. Let's try and see if we can reproduce that with a ray diagram. With every ray diagram, you select particular rays to draw. Am I going to draw every ray that is emitted by the person? No, because there's an infinity of those, and that would take too long. So I'm going to go to the top of the head here, and I'm just going to draw a couple here and there, and you'll find that that's going to be the way we do things. We're going to select particular rays as we go along, despite the fact that the top of the person's head is essentially kind of acting like a point source and is emitting light in all directions. Okay, I'm just going to focus on the ones that are going this way and hitting the mirror and then bouncing off. There are other ones, but I'm not going to be interested in those right now. Now, here at the very top of the head, I'm going to put a dot right there, and I'm just going to say, all right, I know the law of reflection means I have to draw equal angled things. So if I draw, for example, a ray which is going to enable the person to see the top of their head, that means that the light has to hit them in the eye, which means that the light from the mirror has to come at an angle from the top of their head here, hit the mirror, and then come straight down to their eye. All right? So here's what this is kind of going to look like. And I'm going to do my best here to do this in this will be a reasonably straight line, I think. We'll see. All right? So like so. Close enough for government work. This is the beam of light that enters the person's eye, which means they are seeing the top of their head. Okay? Now I'm going to do one from, say, their waist here. Well, actually, no, I'm not. I'm going to do a different one from the top of their head, but this one we're not going to see. This one's going to go off in a couple of different directions. So here's what we'll do. I'm going to stay with this point here, and I'm going to let's see where that's there. So if I go here, okay. So another outgoing ray from the top of the head looks like that. Oh, missed. I missed that one. Let's try that one over. so. All right, and there's another one from the top of the head which is going down this way. Let's go and hit about there. So that means going about down there. Okay. So I've got a couple of rays just off the top of the head. Notice only one we see is the one that hits us in the eye. These two we don't end up seeing. However, they are light rays that are reflected from the mirror over our head and down towards our feet. Okay? The question is, where does it look to the person like this light is coming from? Now, remember yesterday when I talked about the principle of least time with reflection, and we talked about the billiards problem, where, if you recall, I had point A and point B, and I said, well, we've got a mirror here, and if I want to geometrically construct the path of shortest distance from A to mirror to B, then all I have to do is geometrically take this point, 1, 2, 1, 2, and construct an image point down here underneath the mirror, or kind of like inside the mirror, and draw straight to that one, right? Like that. And I called that B prime. Of course, B prime is not actually emitting any light or receiving any light. What's happening is the light is hitting the mirror and then going up to point B here. Nonetheless, if I were to then reverse the path, and light's path is always reversible. If I say light comes in and hits here and goes that way, then I could easily take a light source here, have it come in and hit this way. So I could take the light source and put it at B and have light be exactly reversible, and the light would hit at A. However, if it's us who are standing at A looking at the light, where does it look like the light came from? It looks like it came from B prime, inside the mirror. So when you see yourself in a mirror, you see someone which seems to be standing behind the mirror. Is there actually a person that looks like you standing behind the mirror? No. Our brain knows this and says, oh, it's just a mirror, and I can see there's some surface imperfections. I can see the surface of the mirror. A perfect mirror you couldn't see the surface of, right? So it looks to us like the light is actually coming from B prime going to A, all right? And the same is going to be true here with this reflection over here, all right? So what I'm going to do is I'm going to think about these diverging rays, and I'm going to say, where does it look like they came from? It looks like they came from somewhere back here. If I created a point source of light and put it behind the mirror and removed the mirror, would I be able to see light coming from that source as if it was exactly on the same path? And the answer is yes. Okay, so what I'm going to do is I'm going to trace these back. Maybe that's why it's called a ray tracing. I just found something out. I'm going to trace these back to find where it looks like I would put a source in order to get the exact same path of light. All right, so light traveling in straight lines means all I have to do is go straight backwards here, like that. I'm going to come up with this one, like that. The one that hit the person in the eye is going from this direction. Okay. Now, what am I doing? I'm tracing backwards the rays that have been reflected by the mirror. Okay, this is often a common not misconception, but it's a common mistake that people trace the incoming ray that way. But it's not doing that. We're concerned about the bounce, the reflected ray coming off. Where does it look like the reflected ray came from, right? This ray up here is due to a reflection of this one that was going that way. So once it comes this way, our eye is going to see it, and we're going to say, where does it look like it came from? And we're going to trace that path all the way back.
okay? Now you'll see that I just traced them and they intersect right here, which means that it looks like all of these three rays came from a point right back here, okay? This is known as the image point. This is where the image of the top of the head is for the person in the mirror, right? So if I took any other point on the person, I could go to their arms, their waist, their feet, whatever, and I did the same thing and drew rays bouncing in off the mirror and coming out, and then traced them back, I would find that it looks basically like this. Okay? You'd be able to see yourself. This is why you see yourself in a mirror, because your brain knows what the mirror is. So the light entering your eye is slowly diverging, right? It's going like this. Of course, neither of these actually hit me in the eye, but imagine that we're talking about really tiny, itty-bitty deviations in the light rays, because they have to enter your pupil, right? So I'm thinking about the light coming in like this, but they're slowly going away from each other as they hit my eye, which means that when they focus in my eye and my eye sees an image like on the movie screen in the back of my retina here, then it sends that to my brain, and my brain says, well, it looks like they're coming from over here, exactly as if there were no mirror and there was a person standing here. And that person was an identical copy of me. All right. So you'll notice a couple of things about this. It's a kind of a fun situation. The height of the image and the height of the object. Height of the image, this is the image right here. A couple of words. That's the image. This is known as the object. I'm going to put that over here. There's the object. The height is the same. Image height and the object height seem to be the same. This is what you get from a ray diagram, an approximation of what does the image look like. But of course, we already know what the image looks like. We've seen ourselves in a plane mirror, and you don't get any distortion. You just get an exact replica of yourself. So the image is the same height as you are. And furthermore, you'd find, although it looks like it's not quite right, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, almost, not too bad. But if I looked at it with a more practiced eye, then I would say the distance here from the mirror to the object, this is known as the object distance. And the distance from the mirror to the image, this is known as, cleverly, the image distance. You'd see that they are almost the same. If you were looking in a plane mirror, they would be the same. You'd find that that's about the same number. All right. When we talk further, we're going to find that the object distance and the image distance are important quantities. All right. So I'm going to call the object distance P and the image distance Q. You will find different conventions on this. You will find them called S and S prime, D sub I and D sub O, or just I and O. I can't use I and O because in an equation it looks like you've got a zero going or an imaginary something. So I'm just going to go with P and Q. They have basically no other meaning. Well, momentum, but that's okay. We're going to go with P and Q for this. The heights I mentioned already. The object height. We're going to call that H. We're going to call the image height. We're going to call that H prime. And if we thought about the comparison of the heights, I'd be able to say, well, there's a magnification involved. Except here, there is no magnification involved. Which means that, in fact, instead of the magnification being 0, in this case, the magnification is actually going to be 1. right? So in other words, the thing is the exact same size as the object. The thing being the image is the exact same size as the object. That's a magnification of 1. Okay, so we're going to start introducing some terminology and some quantities here. Magnification is h prime divided by h. That's the image height divided by the object height. Okay. Okay. A bit more of terminology. We've talked a little bit about, okay, the rays made by the reflection from the mirror, the rays coming this way, are physically identical to rays that would have started from a point here and just spread this way as if there were no mirror here. Okay, that is an identical path. We know that there is a mirror here. And we know that there is no light behind the mirror that's coming through the mirror and taking this path. We know that the light is reflecting and all the light is contained to this side of the mirror. There is no light on this side of the mirror. So we have to come up with a way to discuss this image because images can be different. There is an image that is actually due to light converging to points, but this is an image that's due to light appearing to have come from a point behind the mirror, and that's not physically possible. So we give this image a name to tell us that this image is not constructed by actual light converging. This is due to us taking light that is diverging and assuming that it came from a point back here. All right? So this is a name that we call these types of images, and it is known as the virtual image. Okay? The virtual images are always produced where no light actually exists. Okay? The virtual images are always due to us taking the diverging rays and saying, what would happen if I traced them back and found where it looks like they could have come from? Right? The virtual image is not made by actual light coming from a point. There is no light at this image. Okay, this is, and I hate to belabor this issue, but because it has this kind of mystical name of virtual image, you say, well, is it actually there? Yes. Is it really? No. Okay, so what are we talking about? Well, we're talking about our brain seeing light that is diverging and creating an image, right? And taking those light rays that are physically traveling along the same path as these light rays and saying, that's exactly the same situation as if I had just reproduced myself, put myself there, and thrown the mirror away. Exact same situation. We couldn't tell the difference, okay? So this is a virtual image because light is not actually over here on this side of the mirror. Okay? All the light is contained on this side of the mirror. So this is a virtual image, and it is not created by light. It is created by us pushing the light's path backwards to see where does it look like it came from. It's over there. Right? No light is actually here. Okay. So that's cool. We have this issue going on here, and we have the ability to analyze plane mirrors now. Okay. The fun thing with plane mirrors is that once you have the ability to look at one of them, then you can make collections of them. What happens if I have two plane mirrors? And you say, well, what good is that? Well, what would happen if I put a mirror and instead of
instead of, let's see, if I put a mirror like here, what if I put a mirror like there? And I took all these light rays that were coming up and bouncing off this mirror and going to this mirror, and now they're bouncing off this mirror. Well, I would just say, okay, the reflected angle equals the incident angle. We know that that's the law. I would take, for example, this ray right here, and I would say, okay, I'm going to draw a normal to this path. I'm going to look at this angle right here. I'm going to make that angle right there, and the outgoing ray should be going this way. All right, so I'm just going to start bouncing rays off mirrors like this, and really it's all geometry. It's all about angles. Okay, it's all about the angles. So the angle of this mirror compared to the angle of this mirror, and the angle of this outgoing ray compared to the angle of the incoming ray, and etc., etc. You're just tracing. You're chasing the angles around. Okay, so when you have multiple plane mirrors, that's effectively what you're doing. And you'll have a couple of chances to practice that on the homework. So let's go on to a curved mirror situation. This is fairly straightforward, I think, because everybody has so much experience with the plane mirrors. Let's go ahead and take a look at the curved mirror situation. All right. So let's see here. Here's a plane mirror, right? And you'd say, well, okay, that looks like that looks like kind of weird, right? It looks like somebody way back there because they're so small and they're emitting light coming this way. Now we're going to take a look at a curved mirror. Let's see here. This is, where's it pointing? Oh, there it is. This is your little funhouse mirror. Whoops, there we go. There's your funhouse mirror. Right, so if I get really close, then you can see a little bit better. This is probably not what you want first thing in the morning, so I hope you're seeing this at some point later in the day. And of course, if I take this and turn it the other way, this is also silvered. We were just looking at the at this side of it. Now if we look at this side of it, it goes that way. And I gotta find a way not to, there we go. Okay, and there's what it looks like with that side curved. And if I turn it around and I do this side curved, but I'm going to bring it back a little bit. And now something interesting happens, right? Now something interesting is happening. I'm upside down. But if I go a little closer, oh, look at that. I'm right side up again. This is a fun thing. Oops, wait, hey, there we go, right? Whereas if I take this side of it, whoops, where are we? There we go, come on. I go backwards, you see, I just get squished looking. Come on, stay there. I just get squished looking as I come in further and further and further and further and further. I don't change, right? I'm not changing my orientation like I did in the other side of the mirror. So this is interesting. Why the change? If you've ever looked at yourself in a spoon, then you will have found the same type of thing. Now, we talked a little bit about object distance, image distance, object height, magnification, that type of thing. We're going to take all of those terminology words and we're going to go to a curved mirror. Let's start with the one in which I don't flip over, right? So in other words, that's a situation where I have a mirror that looks like this. And I'm over here. Remember, I usually draw the object on the left side over here. And furthermore, I'm going to put this object in the middle of the mirror. Now with the plane mirror, I had the whole mirror like this and then the ground. In this case, I'm going to keep the mirror kind of in the middle, or me in the middle, or how, I don't know quite how you think of it, but like I'm just going to create myself a little axis right here such that it's symmetric top and bottom. In other words, the tangent to the mirror is vertical at that point. Okay, so that makes this axis horizontal. This is known as the optic axis.
You'll probably never see those words again in this class, I don't think. But anyways, we're going to consider objects on that axis. So imagine that instead of a person now, we have something like a flame, like a candle or something. We're holding the candle right here. Okay, holding the candle right here. Now, here comes a few more approximations. I'm going to approximate the height of this candle as being fairly small. In other words, what I want to do is imagine that this mirror is an arc of a sphere, okay? Or if you like, because the way we drew it, it's the arc of a circle. This is known as a spherical mirror. But that doesn't mean it's an entire sphere, it just means it's an arc of it, okay? Or I don't know what you call the solid angle part of a sphere. It's an arc. It's the arc of a circle. The way we draw it, it's the arc of a circle. What we're going to do is assume that the curvature, it has a big radius, okay? And we're going to assume this height is fairly small so that the rays of light emitted by this thing that we're going to trace, there I go again, that we're going to draw hitting the mirror are essentially can be imagined to be very close to this axis. That means that when you think about what I was talking about yesterday, where one of the great uses of Fermat's least time is that if you want to focus light to a point using a mirror, remember this? It's a paraboloid. Or a parabola was the way I drew it, but it's really a paraboloid. Okay, so these big radio telescopes that they have, or the big giant, like the Keck telescope, or the Peak telescopes, or the Palomar, or any of these are all parabolic shaped. Okay, they're all parabolic shaped because they all have the property of taking any light that's incident upon it, that's falling from a great distance, right, from some very far away, and focusing it to a point. So if you look at a parabola, the curved bit is very much sphere-like, it's very circular-ish, but then the parabola has a very distinct different shape after that. So if you try to do the same thing with a spherical mirror, you're going to fail, because the light as you go further away from this axis, the light out here does not focus to the same place as the light in here. Okay, that's called aberration. It's a well-known phenomenon. It gets studied. We're going to circumvent that problem by not thinking about the light that's way out here. We just want the light that's in here close to the axis. All right. So this mirror then has a radius. All right, so I'm just going to say, where would that be? Probably looks like it's about here. I'm going to call that the C point because that's the center of the circle. That's the place where I would put the compass point in order to trace out this arc with my compass. Okay? Now, this is kind of a funny situation because I'm starting with one like this, but if I take a look at the rays of light again, okay, so I'm going to, once again, the candle gives off light in all directions. I'm only going to pick a few different rays to concentrate on, all right? I'm going to first pick the one that just comes in straight. It's parallel with the axis. There is a ray that does that. This one comes in parallel with the axis and hits the mirror right there. Now, we know that that is going to get reflected upwards because the tangent of the mirror right here at the axis is vertical. And so if I go above it, you can see the tangent is going to be sloped a little bit. And so where the light hits it, it means it's going to reflect off and go that way. Okay. The question is, how much that way does it go? Well, interestingly, since I'm going to obey the law of reflection here, I'm going to come in here, I'm going to draw my normal. I'm just going to drop my normal at that surface, at that point on the surface right here. And I'm going to say, well, the angle out should equal the angle in. So how much is that? It's going to be about that big. It's about that big, so it's going to go from about there. And it's going to go this way. Okay, remember these are qualitative. You will not have to do this normal drawing and whatnot in order to try and find where this, because I'm going to give you a special hint right now as to where this ray comes from, or actually where it looks like it came from, right? This ray right here looks like it came from a point on the other side of the mirror, like down here, right? Okay, that's a special point on the mirror. I'm going to trace that outgoing ray backwards. So we're going to say, if I trace this backwards, it looks like it came from a point right here. Well, this is not quite to scale then, but that's okay. Yeah, I kind of got this a little bit that way, but that's okay. Remember, these are qualitative, so you'll eventually get through doing them pretty well. It looks like it came from that point right there. Now, this point is a special point, okay? And it is the point where incoming light that is parallel with this optic axis looks like it came through, when it reflects, it looks like it came from this point. Okay, no matter where on the mirror I am, and as long as I'm kind of right, we're still talking small, close to the axis rays here. Even though I might not draw it that way sometimes, we're always assuming that. In fact, that's so important. I need to write that over here. We're assuming that rays are all pretty close to the axis. And this has a name, it's called the paraxial approximation. Okay? In other words, all of the rays are parallel with the optic axis, parallaxis. So what I was in the middle of saying was any ray that comes in parallel with this axis, and of course is close to the axis, right? Any ray that comes in parallel will get reflected and will look as if it came from this point. So I could equally well have drawn some other incoming light, not from the candle, but something else from in here, and it would have bounced off. And had I just kind of dotted it back here, it would have looked like it came from this point. This point is known as the focal point. and is a special point. Okay. In other words, it has a relationship to the radius of the mirror, one which is not very well represented here, but should be half the radius. I'll show you that in a minute. All right, the radius as I've drawn it is all the way out to here at point C, so I messed that up a little bit, but remember these are qualitative. So I guess what I'll do is I'll just kind of scoot this point maybe in over here. We've got a half and then 1, 2, 1, 2 and a half. So the center point's about here. There it is. Now it's perfect, just like I drew. And that would be the radius distance, right? This is the center point, so the radius is that distance out to there, and the focal point is about half that distance. And we'll get to that as to why that is in a little while. When you draw a curved mirror, then this is what's called a principal ray. It's a principal ray because it comes in parallel and therefore leaves via a focal point. Okay, this is a principal ray. There are basically 3 or 4 principal rays, and these are all we need in order to make an image and figure out where is this image going to be. and what's its orientation going to be. So I'm going to draw another one and see if I can find where another ray that comes in and bounces off, when I trace it back, where is it going to be? Is it going to intersect this right here? Because if it does, then I'll know that the image is right at that point. Right? As soon as I have two trace back rays intersecting, I'll have the image, because that'll locate it for me. So I'm going to pick another principal ray, and this one is going to be one in which it's aimed at the vertex point right here, where the tangent to the mirror is vertical. Therefore, I know that whatever angle that the ray comes in at, it will leave at that exact point, because it's hitting basically a plane mirror right at that point. Okay, so I'm going to take this point right here, and I'm going to say, all right, ray comes this way like that, and therefore it's going to leave coming out about here like that, such that these two angles are equal. Well, they're always that way, but it's easy with this one because it just bounces in, bounces out. Now, again, I have diverging rays that have been leaving the mirror. I have these diverging rays here that are leaving. If my eye, remember these diagrams are always kind of exaggerated. So if I have an eye over here and I'm looking at it, these light rays are coming into my eye and they're spreading out like this. Therefore, my brain goes, where does it look like they came from? Dot, 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 dot. I'm going to go back and trace them back and find out that if I go like this, backwards, right there is where it looks like they crossed, and therefore there's the tip of the flame right there, and the candle is here. This is the image. Right there. I don't know if you can quite see that. Okay? That's the image right there. Of course, this is the object here. And so we'd have the object distance and the image distance. Now, where are we going to measure those from? They're going to be measured on the axis. So that means the object distance would be from the point where I just bounced this ray all the way over to here. And if I kind of said, well, it's from here, I would take this point here and I would go, it's from there to there. That would be my object distance, which we call P. My image distance, which we're going to call Q, is going to go to the image here. And I'll just draw that there. That's Q. When we say it's the distance from the mirror, we are always talking about where the mirror crosses the optic axis. Or really, it's the other way around, where the optic axis crosses the mirror. That's the point where we're measuring P and Q from. Okay. Okay. Again, we're going to notice a couple of things about this, and I'd like to now start introducing you to the 4 questions. The 4 questions, let's see, I need this room, so I'm going to erase that. The 4 questions are very useful, not just during a certain time of year, but whenever asking about the qualities of an image formed by a mirror, and subsequently later on when we talk about lenses, we'll ask the same 4 questions. And the 4 questions are as follows. These are what we want to answer in order, with our ray diagram, we want to answer these 4 questions in order to try and give us a qualitative look at what the image is doing. What are its characteristics? Okay, so number 1, where is the image? We're going to ask ourselves, where is it? Is it in the 2 cases we've done? The answer to that is it's behind the mirror. In this case, it's behind the mirror. Okay, number 2. Is the image real or virtual? How much more room do I have? I can write it here, can't I? Did I make it? Oh, I did. Is the real image or virtual? Now, you can maybe start to understand that these two questions aren't independent of one another. If the image is behind the mirror, there is no light over here. So the image cannot have been made by light. It's not really the right way to say it, but it's not made by light going away from a point. It's made by light diverging off the mirror surface. Okay? As soon as we start going behind the mirror, we have to have a virtual image here. Therefore, any image that is behind the mirror is virtual. So these two are not always independent from one another. They're not always. They are not independent from one another. They are linked. Yet it's useful for us terminology to say, is it a real image or a virtual image? As soon as you know it's a virtual image, you know, oh, I know it's not an actual image. It's just one that's behind the mirror. Okay. Number 3. Is the image upright compared to the object, or is it flipped over? Is it upright or inverted? So when we ask that question, it's always in relation to the object. If I had a candle which was upside down here, I would get an image which is upside down here. But it would be called upright because it has the same orientation as the object does. Right? If it's this way, then it's called upright. If it's this way and this way, it's still called upright. Okay? It's only when you have this and this that you have inverted. Likewise, if you have that and this, still inverted. This image is upright. Last question. And I don't know if necessarily this is language that is in common usage nowadays, but is the image magnified? Is it greater than is it greater in size than the object? Or is it smaller in size than the object? And for that I use the word minified. Is the object greater in size, exactly the same size, or lower in size? And from our ray diagram here, I think you can see this is a lower in size object image. Therefore, this is minified. The ray diagram gives us the answers to the 4 questions. Every time you draw a ray diagram and you're wondering about the image, draw the ray diagram and look at the answers to the 4 questions from the ray diagram. You can get them right away. Okay? And when you do that, it helps you figure out a lot of things about what the image qualities are. And for most of the part, this is what we're after for right now. Okay? Alrighty. Now I'd like to get on to the reverse of this. This is, by the way, known as a convex mirror, but I don't like the word convex. I'm just going to call it a diverging mirror because the rays that come out of it are diverging. This type of mirror has many uses, not only in at the boardwalk and in fun houses throughout the country and world, but also appears as the passenger side mirror on cars due to the fact that it gives a wider field of vision. And that is the reason you will see on the mirror the words printed something like objects, which is, it should be images. The image is small, right? So it says the objects are further away than they appear. Further away than the image is telling you, okay? Because whenever you have a diverging mirror like this, the image is always smaller than the object. So what do we associate with that? When I see something that's smaller, I go, oh, it's further away, right? If I move that back here, now they're the same size. So it's just further away. When I look at it in a mirror and it's smaller, the image isn't further away, it's just smaller. It's actually kind of close to the mirror. So when you look at an image from a convex or a diverging mirror, it's not that the image is really, it's way over that. No, it's not. It's just reduced and it's right here. Okay. All right, so let's take a look at the other type of mirror, which is known as the converging mirror. I'm going to have to completely redraw this. So we are going to just do this and that. And then I'm going to take these, I'm going to leave the 4 questions up. But now we're going to answer them for this situation. Okay. So now I'm going to take the same type of thing here. Like that. And have my optic axis about there. Well, that does not look symmetric. Let me try that again. That does not look symmetric. Maybe that's a little better. The optic axis intersects here at that point. That's the vertex point where the tangent to the mirror is vertical. And again, that's the point where we're going to be measuring all the distances, and we are still assuming the paraxials, and this is going to be throughout the entire, this is one of those assumptions that goes throughout all of geometric optics. Okay, so here I would have a center point. Now the circle, instead of being on this side, is flipped this way, right? So my center point, let's say, is over here. Let's say my center point is there. And therefore, 1, 2, 3, 4, 5, 6, 7, 8. Oh, good. 1, 2, 3, 4. My focal point would be here. I'm going to label that F for the focal point. And I'm going to put an object out here. Let's suppose that I have an object, say, here. Again, my candle. And my candle is outside the radius of the circle, outside the radius thing. That doesn't matter. That's just like, it's just somewhere. And I'm going to consider the paraxial rays. So, principal rays, number 1, goes in parallel with the axis. So here comes number 1. All right, it's going to hit right there. Again, I can create the normal and do the angles and stuff like that, but geometrically, I can show any ray that comes in parallel with the axis exits through the focal point, or, remember when it was a diverging mirror, it appears to have exited via the focal point. I had to just trace it back to find out that that was the case, right? But in this case, it's right in front of us. It's going to hit here, it's going to reflect right through that point. Okay, like so. Again, I can take the same ray as I did last time, one which hits the vertex point, goes in and comes out at exactly the same angle. That's a fairly easy one to do. Let's see, we're going to do 1 and a little bit, so there. So I'm going to take this one, I'm going to go into here, like that. Okay. Now your ray diagrams do become a little bit of a jumbled mess of rays going in and rays coming out. So like I said before, it's important to concentrate on the outgoing rays when you try to determine where the image is. Now this one is going to come out from there and it's going to go out to here. like so. Not quite right, but close enough. And you'll notice something. I don't know if you can quite notice something. It's a little bit of a not dark enough ray here, so let's try that again. Okay, maybe you'll notice something. Those two rays, this is the diverging one from the first ray right here. This is the diverging one from the second ray right here, but they're only diverging here. What were they doing back here? Look, this ray comes in here like that. Well, you can't see because of the shadow that I'm making. All right, so this ray comes in like that, comes off the mirror this way. This one comes off the mirror this way. They hit each other. They keep going through each other, which is fine, but they cross. That's important. That's where the image is. Now, the image is here. The image is there now. I'm not sure if you can quite see this, so I'm just going to lift you up and bring you in a little bit. Maybe. There we go. Come on. All right, so here's my, here's my ray diagram. The image, so what I'm getting at here is that the image is formed by the rays that are actually crossing. This ray that came in bounced off and came that way and is getting crossed by this one coming in here. Where they cross is where that image is formed. There is no tracing these backwards because look, they aren't diverging from each other when they hit the mirror and bounce off. They are not diverging from each other. Therefore, there is no reason for us to have to go behind the mirror for these. This image is in front of the mirror. This image is also flipped over, which is what we saw when we looked at the, if you've ever looked in a spoon, or when I showed you the other one, the image is flipped over, right? There's a point where it's upside down compared to me. Therefore, this is an image that has been made by actual crossing of light. This is an image formed by light. This is a real image. This is a real image. Light has actually crossed to make the image there. Okay? Now, here is a big fundamental difference between a virtual image and a real image. You would ask, could I put a screen here and see the image on the screen? And the answer is yes. Because light would be hitting the screen, creating the image, and then diffuse reflecting off, right, in all directions. Whereas with a virtual image, remember, those are always behind the mirror. If I put a screen there, there's no light there. So I can't see that. This is a great way to, in your mind, to say, is this a real image or a virtual image? Put a screen there. Would light hit it and make the image? And if it's yes, then you've got one of these and it's a real image. Now, where is the image? In this case, it's in front of the mirror. Is it real or virtual? We know it's real. Notice how both of those changed. If it's behind the mirror, it's virtual. Has to be. If it's in front of the mirror, these have crossed. I can't trace rays back and have an image in front of the mirror. So if it's in front of the mirror, it's real. Is it upright or inverted? This one has the opposite orientation of the object, so it is inverted. And we'd ask the question, is it magnified or minified? This is a tough one, not in this case, but it's a tough one to sometimes see from your ray diagram, but this is minified from my ray diagram. This is a minified image. All right. So notice, we've only done 2 ray diagrams here, but notice that there is a correlation. Behind the mirror, virtual. In front of the mirror, real. Now notice one other thing. Behind the mirror, virtual, upright. In front of the mirror, real, inverted. These kind of start to go together, and you'll see this with time and experience. Think about it. I can't have an upright image if kind of the light's path this way is going to be directed downwards, right? The light's path is directed this way. It can't be an upright image. It's going to be inverted. And this is a hallmark of the real image formed by what's called, in this case, a converging mirror, or if you like, concave. Okay, let's talk about sign conventions, because part of that is on the PLC this week. So, the sign conventions, they are directly related to the answers to the 4 questions. If the object is in front of the mirror, this is called the positive image distance. Actually, is this negative, positive? Yeah, I believe I asked something about negative magnification, so we'll get to that in a minute. This is called positive image distance. Okay. The answers to these 2 questions come from the magnification. And I'll get to a little bit more on this in a minute. The answers to these 2 questions come from the magnification. If the object is upright, we're going to call that a positive magnification. If it's inverted, we're going to call that a negative magnification. Okay? This is a negative magnification. Whoops. Negative, capital M. Because I defined M for you already. If it's flipped over, it's called negative. If it's upright, it's called positive. And remember, even if they both are quote unquote upside down, right? If they're both upside down, the image is still upright and therefore would still have a positive magnification. If it's minified, then the magnitude of the magnification is less than 1. This goes right back to the plane mirror. I had a magnification of 1 because my image was the same size as me. If it's smaller, then I have a magnification less than 1. So I'm going to say that the absolute value of the magnitude is less than 1. The absolute value of the magnification is less than 1. Okay? If it's greater than 1, it's magnified. Right? Then the image is larger than the object. If the object is upright and the image is upright, I have a positive magnification. It could be magnified and positive. It could be minified and positive. Look back at the last diagram we did. That was a positive minified image. This one is a negative minified image. Okay, so the magnification actually gives you 2 pieces of information, depending on is it positive or negative, is it greater than 1 or less than 1. All right, those are 2 things to think about with the magnification. Let's talk again about the image distance. The image distance is here. Okay, the object distance is positive. Okay, if it's to the left side of the mirror, I say the object distance is positive. Since the image is also on the same side of that, we'd say it's positive. And if the image was behind the mirror, we would have said it's negative. And therefore, if I have a virtual image, I'll have a negative image distance. Okay? Now, here's how I think about it. I don't try to remember a bunch of sign conventions for this, because they're going to flip around as soon as we get to lenses. So what you want to say, right, is then, oh, it's like there's an axis here and this way is positive and that way is negative. Okay, fine. But when we get to lenses, you're going to have to change that. So I don't like to do that. So here's how I think about it. The image distance is positive if the light is doing what it's supposed to be doing. What does the mean? Okay, so this is a mirror. Where is the light supposed to be? The light's supposed to be over here. It's supposed to be doing things. It hits here and comes back. It doesn't go this way. It hits and comes back this way. And therefore, if it creates an image on the side that it's supposed to be doing things, then I call that positive. Note, I will contrast this with the lens. What happens, what's light supposed to do for a lens? It's supposed to go through the lens. Therefore, if light's doing what it's supposed to be doing, the image should be on the other side of the lens. You see how this is going to flip if you say, oh, left side's always positive, then by the time you get the lenses, you're going to have to say right side's positive for image distance. But if the light's doing what it's supposed to be doing, which is bouncing off the mirror and then making an image over here, then we're going to call that positive. If it's bouncing off the mirror and not making an image here, but I find the image on the other side of the mirror, well, that's the wrong side of the mirror. There's no light over there. The light's all over here. That's negative image. Lens works the same way, right? If I shine light to a lens and the light goes through the lens and makes an image, that's a positive. If light goes through the lens, diverges, and then you have to go, where's the image? And it's over here. That's the wrong side of the lens. The light's over there. What are we doing over here? Negative image, virtual. Okay, so that's how it plays together. Keep that in mind, and we'll go from there. Okay, so we've got this. What I'd like to do for you is just show you. Gee whiz, I don't think I really have time to do this because we have to kind of come up towards the end of the class here. This is, after all, geometric optics. So what I would kind of like to do here is think about the triangles and using similar triangles. And so one of the triangles we can use is made by this vertex right here, the vertex one. So if I take a look at that, there's a height. Right? I'm going to try and darken in this triangle so you can see it. Right? Like that, and then like this. You kind of see that triangle? It's got an angle right in here, which you might call theta. Okay? If I make that triangle and then I make the subsequent, its reflected triangle right here, that would be down here. Okay? But you'd know that has to be the same angle because remember, the ray coming in hits the mirror, but the mirror is basically tangent vertical at that point, so the outgoing ray is exactly the same as the incoming ray. So both of these angles are exactly theta, say. Therefore, their tangents are equal. And I'll just kind of outline this really quickly so you can look at it. But the tangent of theta, if I think about the big triangle here, the tangent of theta would be the opposite divided by the adjacent. And the opposite is the height of the object. And the adjacent side is the object distance, p. But that same angle should apply to this triangle here. And so that should be equal to the image distance, but note this image is flipped over, so we've got the convention that if it's flipped over, it's negative. So we're going to call this a negative h prime in order to make the sign positive again. And it's going to be divided by the image distance, q. Okay. And therefore, if I wanted to consider, how do I find the magnification? The magnification is defined to be h prime divided by h, right? That's what I told you before. So if I just form h prime divided by h from this, what I'm going to do is divide h underneath here and then chuck the minus on the other side. I have to move the q up, so I'm going to find that this is equal to negative q divided by p. This is going to be a really useful situation to figure out the magnification. Q over P, we typically will be able to find the image distance and we should already know the object distance. In some cases we need to find it, but more or less we can find those two quantities much more easily than the heights of the two things. Usually we'd use the magnification to find the heights, okay? Unless we were given those, and then we would know what the magnification was, all right? So that's a really useful thing, okay? Also, from some more geometry involved here, what I'm going to do is make another triangle involving the center point. Okay, so one of the funny things about the center point, I told you there was 4 rays. We've only gone through 2, and that's really all you need is 2. But here is the center point, C. Okay, if I consider the triangle made by a ray going through C, it's going to look like this. Oops, right through there. And it's going to hit somewhere down there. Okay. Now, if I consider the triangle made here, and I have missed that very badly. I'm not going to consider the triangle made by that because that is horrendous. Okay, let's try this again. I'll get it one of these days. That one was not good enough for government work. So let's try this again. I'm going to go from here to here. Right, and then from here to here. Ooh, close, I'm missing it. That's okay. That's worse, but that's okay. It's supposed to make big dots. It's supposed to be right on the image point right there. It's supposed to go through that. So look at this angle here that's made by this triangle. Call that alpha. By parallel angles, those two would be the same. And therefore, if I looked at the tangent of alpha, and once again, since you're far away, let me just move you in a little bit so you can see this a little bit better. Okay, I'm considering the ray coming from the top of the candle going down through the center point, C, and then bouncing off the mirror. Spherical mirrors have the unique property that if you go through the center point, you're going to bounce directly back along that path. So this ray should hit the mirror, come directly back along where it is, and then help form the image right here. Okay, so I'm considering right now this triangle right here and its opposite right here. Those two triangles right there. Okay. So if I consider those two triangles, I can do the same thing, take the tangents of those angles, and maybe we'll finish this off next time, but I come up with a way to relate the image distance to the object distance. Okay, so if I do that, I'm going to have tangent of alpha equal to h divided by p minus r, because the center point is at the r distance, and that should equal negative h prime times r, but minus q, like this. Okay, now, since we're just about out of time, I'm just going to tell you, and maybe we'll finish this off early next week. I'm just going to tell you that if you take these two things right here and combine them, what you will find is that we get this relationship. Right? We're going to take that and we're going to take that. And they combine to give us this thing right here. This is how the object distance and the image distance are related, and F is the focal point. Remember, F is half of the radius of the circle. So that when I think about an object having a 10 centimeter distance, and the focal length of the mirror is, say, 5 centimeters, then I can figure out where the image is going to be.
real quick example of that is going to look like this, right? Suppose the focal length is 5 centimeters, but my object distance is 10 centimeters. Okay, if I put those two in here, what I'm going to find, I'm going to look for the image distance, and I'm going to find, remember these are always reciprocals, I'm going to find 1 over the focal minus 1 over the object distance. This is going to be 1/5. That's going to be basically 1/10, right? 1/5 is the same as 2/10, so this is going to turn out to equal 1/10. That's 1 over Q, which tells me that Q is equal to 10 centimeters. Right? In other words, the image is right on top of the object. They're at the same point. Reason being, the object is located right at the center point, and the image is going to be located right at the center point. Notice what happens when I take the magnification, though. Negative Q divided by P. Q is 10 centimeters. It's positive. This is a tip-off to the 4 questions. The image distance is positive. This means the image is in front of the mirror. This means it is a real image. Okay? I should therefore expect it to be inverted, so if I look at negative Q divided by P, I've got negative plus 10 centimeters divided by plus 10 centimeters. That's -1. That means the image is the exact same height as the object, it's just turned over. It's inverted. Okay? So the magnification would be -1 from that. And since I'm a little over time here, I'm going to stop there, but we will pick up talking about curved mirrors and how to find their images and characterize their images. We will pick that up on Tuesday of next week. So, in the meantime, I bid you happy weekend. These are our only 2 classes this week, and so we will pick up next week and go from there with more on the formation of image by mirrors. And so I say farewell and happy weekend to you folks. Enjoy maybe a little bit of clear weather. See you next week.